Alright, this is Emily Ferreira, and I'm doing test corrections for 1976. This is part 1, and I'm doing C now because I have to do A and C for number 21, but I'm doing C first since I already started it. So, for C, you're looking for initial thickness, or you're looking for the thickness that the bullet, the block will have in order to stop the bullet in terms of initial thickness. So, from your first kinematics derived equation, you have v squared equals vi squared plus 2a delta s. And then you know the two equations that you get for A will be v naught over 2 squared minus v naught squared over 2 L naught, and also this is just rearranging the equation, negative v squared over 2 L nu. So you can make those two equations equal each other, which will then be negative 3/4 VL squared equals negative VL squared over 2 L nu, and this is over 2 L naught. And then you simplify that equation to the end, which is L nu equals 4/3 L naught. And that's that. That's C. And going back to A of 21, because it's a collision, you use conservation of momentum, so V1 M1 equals 1/3 V1 M1 plus V2 M2. This is capital M. And you want to get it in terms of V2 because you're finding the final speed of block M, so rewriting the equation is V1 M1 minus 1/3 V1 M1 over M2 equals V2. And it's 1/3 VI because of the fact that in the equation it said that the bullet emerges from the block with a velocity of v naught over 3. Okay. Now, 22b. 22b. You have to find Gauss's law, or you have to use Gauss's law to determine the electric field. So you know that Gauss's law is Q enclosed equals epsilon times I E, and then you know that I is field times area, so you can, because you need the field, you need to do that, so it becomes EO times field times area, and because it's a sphere, the surface area of the sphere is 4/3 pi, or 4 pi r squared, and your Q is now 2Q because, it was always 2Q because the enclosed, the sphere has a charge of positive 2Q, so it's 2Q equals, and then it would be epsilon times E times 4 pi r squared, and you have to rearrange for E, so that becomes 2Q over epsilon times 4 pi r squared equals E. Okay, that's B. Alright, 22C. When you're calculating the potential difference, you know that potential difference equals the negative integral of the field, and you just found the field, so all you do is take the integral in respect to ds. And all you do is take the field, take the integral of what you just found, so it's equals integral, and it's going to be from r to 3r because the outer sphere has a radius of 3r and the inner has a radius of r, so you need in order to find the potential difference between the two spheres, you need it from one sphere to the next. So that becomes that of 2Q over E naught 4 pi r squared, and now it's in terms of the radius, because now you have an r in the equation just to keep it equal, and you can pull out the 2Q over E times 4 pi because those are all constants. So then all you have to do is integrate negative 1 over r from r to 3r. And then times the 2q that you took out before, 2q over e 4 pi, epsilon 4 pi. And then, or that's, when you took that out, it left you with a 1 over r squared, which would then integrate to negative 1 over r. And so then you plug in 3r, and then you subtract what you plug in for r. And that's what you do. Okay, lastly, d. When you think of the final distribution of the spheres, you know that the inner has a radius, has a 2, what's it called, a charge of 2, and the outer has a charge of 1, a negative 1, I'm sorry. And so when you all you have to do is add those together to equal 1, and you can't have a charge inside the conductor, so this is going to be 0 after you do this, and it'll be 1 because, oh, sorry, you can't see that, but this is 1 because everything leaves until everything inside the connector will leave until it becomes neutral. So the final distribution is 1. Okay. And that was part 1.